All right, recording is rolling. So it is Tuesday, November 8th. I know I showed you guys this a plan yesterday for the coming 2 weeks. Always a little bit dangerous doing that in case of change of plans. In this case, there is a change of plans because with that storm coming up, almost certainly we're going to get Thursday off. There's no official word on that I've seen so far, and there's even a small chance that I'm not going to see you guys tomorrow even. So I for sure want to get in a lab before this hurricane hits. So that's what we're doing today. We're doing collision cart lab. Oh, by the way, your energy grades are on focus. Your energy quiz grades. That's what you turned your quiz in yesterday. They're up there. I got a grade last night. And there's an interim that's due 1 week from now. So grades are about to close and the whole deal. Okay. All right, so just I did get you guys printed your next puzzles. Again, the original plan was to have a day where had you guys set up in teams and you guys help each other out, and I just like walk around and help you guys out. So we're gonna still try to do that, but see how many days we have to work with. But today we're gonna full focus on this collision carts lab. Okay, so you guys got this page in front of you. It's double-sided. Now, I know I always make this point, but I try not to give you guys a pre-made lab template because you guys in AP are supposed to like more figure out things from scratch. Okay. So here's what I say about this is that this might not be a perfect template. There's some questions that I want you guys to investigate that aren't like there's like a special box on the paper for a little question. Like here, got a couple questions. When you guys are colliding these carts, right? Now momentum conservation is a huge thing this week. So see like, hey, is momentum purely conserved before and after these collisions? Okay. But here's another question that I don't have actually a space for on this paper, but it'd be a good thing to investigate. It's like, what is the kinetic energy in the system, say before and after the collisions? Can you guys do 1/2 squared and add up the bits and investigate this question? Okay. So more like use this paper like as a way to guide your give a little bit of structure to the lab. So you say, okay, I kind of see where this is going. Okay. But see if you can answer both these questions. And like this question, change in kinetic energy, maybe you need to write like down here in this space, right, where it's just like a blank space. Okay. So I'm going to do a demo for you guys. I take you over this page. It's double-sided, right? So there's different kinds of collisions you can do, right? We got these two kinds of collisions. I've got the demo set up here. So here, let's do this. Okay. Yeah, try to put this in front of the camera as best I can. Ooh, okay, it's kind of tough because it's got like a 2-point-something meter long track. But if you're watching this video at home, this might make this easier to understand. All right, so I got this really long track going on here. Okay, it's got these screws, and oh, look at these parts. Right, it's like a low friction system. Right, I give it a push and it just give it a little push, and it just goes. Right, maybe there's a little bit of friction, but not very much. It's pretty close to an air hockey table situation. Right, right now. I've taped on magnets ahead of time with these pads, right? So that now, do you guys know North Pole and South Pole? Guys, what do North Pole and South Pole of magnet do? Right, so those are opposite poles, right? Right, so those will pull together. Hey, do you think you could have a collision that's like inelastic? Could you call that inelastic? Right? You might have to know what were the masses of these things. An empty cart is 500 grams, almost exactly 500 grams. Okay, so that's good to know. The magnets, of course, they'll add a few grams, but you can like stack on like this is 500 grams too, right? I could like almost double mass carbide. Just put that right there. Right? Ooh, now it's like twice as massive, twice the inertia, right? So you can take lab masses and very easily change out the masses if you had to do that. And now, what's with the Hot Wheels cars? The only reason there's Hot Wheels cars is because we have these new speed gates, right? I've never used these with this particular lab before, but I think they'll make it easier, but we're going to see. Because remember, these speed gates work really good with the Hot Wheels cars. Right? I think that's what they're designed for, because they fit exactly on a Hot Wheels track and the cars go right through them. Right? So they read the speeds really easily. But I remember when you guys did the pendulum lab, there was, for some reason, it wasn't really, it was really hard to pick up the, like the lab weight going through it. I don't know why, but anyway. So if it helps, you can put Hot Wheels car. Maybe they'll detect the ether for some reason that I don't know about. Okay, right, so that may or may not be helpful. So we got that. If you turn these carts around, okay. We've got the same poles that are built into the carts, so they'll naturally repel. Oh, look at that. And then so it's not scrape it on there. Here we go. Ah, does that look like an elastic collision? Elastic, that sure does look a lot like a Newton's cradle type collision, doesn't it? And the fact that these parts are the same mass right now, a little over 500 grams, like, yeah, it's operating a lot like it. What would happen if I stack more mass on this guy? Now what? Ooh, now it keeps on plowing through a little bit. Okay. What about if I have this guy run into it? Boing. Okay. I think it's a tiny gradient. Let's go on top a little bit. But okay, yeah. Right. So you guys are okay so far? All right. What else I want to say about this? Okay. So these speed gates, they could possibly work to get the speed here. Like if you have a car sitting up here, right, and it runs through and tells you like how many meters per second it is. You guys have used this before, right? I'll tell you what, if you're having trouble using this, or if it's not really working, because I've never tried it this lab with these before, so this might be one of my Bump Griffin ideas. Who knows? Sometimes even I have a bad idea. But we're gonna see. Do you guys see on this track here? There's clearly labeled. There's a meter stick like built into this this track, right? To tell you like how far, like distances. And you guys have your cell phones. You could calculate time. Now, how I've done this in the past, and you might have to do it this way. You guys let me know today. You guys are the trial class, first period of the day. Is maybe you have to see like how far the cart goes and how much time, and you can calculate the speed because you can do distance divided by time. Could you guys do that? Right now, you have to do something like before the collision and after the collision, where they're going to be changing velocity. So you might have to have like several students keeping track of like several things. You know, maybe several speed gates, maybe several stopwatches. Okay, you guys get the idea? Okay. Right, so a little tricky to keep track of everything, but that's why you guys have teammates. All right, then, right, so you guys okay so far with this demo stuff? Okay, because I want to put this to the side and take a look at that paper. All right, that I gave you guys. Remember that lab paper that I gave you is more like just a guideline to get this a little bit of structure, but I want you guys to really have your minds turned on and think about questions like, well, what is the change in kinetic energy? Okay, that sort of thing. All right, so what have I got on this page? So it's double-sided and each side is a little bit different. You guys see one side says perfectly inelastic. Well, that would mean that the parts collide and stick together, right? That's where like it magnets on. Right? And there's pre-collision and post-collision. You guys see that? The left side says pre-collision, the right side says post-collision, right? Okay, so what numbers could you keep track of? Well, there's the mass of each cart. I put grams. You can do grams, you can do kilograms. If you want to scratch off the unit, make your own unit, you can. Okay. I got speed. Now I wrote centimeters per second. You can do that if you like. If you do meters per second, I think that's the default setting for this thing. Then just scratch off the unit, right? Meters per second, right? Like you can modify this, make it your own. Okay. Okay. Now the way I designed this page is I had one of the carts starting from rest, therefore it has zero momentum. You know, if you want to change that too and go a little fancier, then if you want to take out a blank piece of paper and make your own table, make your own lab, feel free. Okay. But you guys know how to get momentum, right? Which is mass times velocity. So the way I originally designed this was set from my computer screen was, okay, if there's one cart at rest, one cart in motion, then the cart in motion has all the momentum. So mass times velocity of the moving cart would provide all the momentum in that system. Okay, those would be a closed system. So got the two carts. And then here's what happens after the collision. Well, if they collide and stick together, that's perfectly inelastic. When they make one giant mass, that's why I say MA plus MB. Like you can just add masses together. Right? If it's an empty cart and an empty cart, it'll be 500 grams, 500 grams, say it makes like 1,000 grams. Okay. Right. So how fast they move together, and then what's the momentum after the fact? Now you guys see this last column, or it's like bold boxes all the way down. So we've got different trials, trial 1, 2, 3, 4, 5, and you can like swap out the masses level, right? Okay. But that bold box is like momentum. Here's the momentum before in the system. Here's the momentum after in the system. And if momentum is truly conserved, and then all I did is just copy pasted this table. I don't know. Maybe it should not even written this because it's just this copy pasted. Okay. Then these numbers should be ideally the same, but realistically maybe just very close to each other. Okay. You guys get that? Okay. How about the other side? Now the other side is just some general collision, right? So maybe probably something closer to elastic, but possibly not perfectly elastic. So if you look on like a scale of types of collisions, on one end you have perfectly inelastic because they collide and stick. On the other end, it's like perfectly bouncy, which is like a Newton's cradle situation. Right? And yeah, so the general case is probably going to be a lot closer to that end. Right? So here, I got the same setup to start with, which is that one cart's at rest, hence I zeroed out this column. Again, if you want to make up your own table, feel free to do that. Right? And the other cart's going to be in motion, therefore you'd have all the momentum. But after they bounce off each other, they're going to have individual velocity, right? And therefore individual momentums. All right, take a little typo. I'm just noticing here. I should have a dark outline around each of these boxes too, because it got two columns for momentum, because each cart will have its own momentum, right? Okay. Now remember, momentum is a vector value. So does that mean if two carts are traveling away from each other, are they subtracting from each other's momentums? Yes, they are, right? Because to the left and to the right, there's a negative sign somewhere there, right? And a positive sign, right? Okay. Right, so you got that. And then if you add up all the momentum, so if you add up these two columns, well, these two cells would go here, these two cells added up goes here, right? And so on all the way down, right? Then you can compare what was the momentum before the collision and the momentum after the collision, all the way down, okay? Ideally, it should be the same, but throw in another question. Check kinetic energy before and after, right? And say, because if it truly is perfectly elastic, then the kinetic energy should also be the same. Okay? Kinetic energy might go down a little bit, but I'll bet here, I'm flipping the page to the other side. Here's the original side with the inelastic. I bet there's going to be a huge change in kinetic energy on this side when they like collide and stick together, right? But check me on that. See if I'm telling you the truth. Okay. All right. Any questions about this? Okay. So again, this is like mostly exploratory. This paper is for you guys. Now, turn this in by the end of class. Okay, just turn this in by the end of class. But we're taking the rest of today. Just collide these carts. I'll walk around, help you guys out. And if I see you guys tomorrow, then we'll continue on the notes. We'll do like balancing this, coefficient restitution. We'll do impulse, but we'll save that for tomorrow. Okay. The rest of today is just for colliding carts and labs. All right. So I'll see you guys back in the lab area.